All right, let's take a look at the 2017 problem set, and we will only be looking at problems 1 and 2 since they've gotten rid of the magnetic fields for this year. So, problem number 1 starts out with a slab of charge. So we will be looking at planar symmetry. They've given us length, width, and depth, and they have also told us that it has positive volume charge density, and the most happy part of this is that it is uniform positive volume charge density. The positive will come in later on. Let's see here. They've told us what kind of shape Gaussian surface we're going to use, and we're going to start out by looking at just the points on the top and the bottom inside the surface. So let's scroll down here and we can get rid of that. We don't need that. All right, let's have that on here. Draw a single vector on each of the dots representing the direction of the electric field at a given point. All right, so at point R. So if we take a look at point R is in the top half of the slab, and all of the positive charge is below it. So the electric field at that point is going to point up. And this should be straight up, not on an angle. Because if you notice, since we're in the middle here, all the lefts and the rights are going to cancel each other out. So this guy should go straight up. And then at point S is symmetrically below it. So if we folded this slab across the y-axis, we would be equidistant here. So however high I made that R, the electric field at R, I need to make the same thing at S, but pointing down this time. All right, B, use Gauss's law. Okay, so for B, let's come over here because we're going to have to write some work here. Gauss's law is Q enclosed over epsilon naught, produces some electric flux, which is measured as the electric field passing through a given area. And for Gauss's law to work, we need that area to be a closed area. Most of the time in class, we just skipped the whole flux part, but for this one, they say we want an expression for the total flux through the Gaussian surface. Well, let's see here. On the right side, they've given us enough information that we probably could use area, but they haven't given us any information about electric field. So using the right side of the equation is not going to work. Let's take a look at the left side. Q enclosed over a constant. Well, they have given us enough information that we could figure out Q enclosed through the Gaussian surface shown. And it looks like they told us that the Gaussian surface is A, and the height, h over 2 and h over 2, that means the height is going to be h for right now. So Q enclosed over volume equals total Q over total volume. So we'll do total, then this guy will be enclosed. Now, they didn't tell us the total charge over the total volume. What they told was this guy. They told us rho naught, so rho naught. So Q enclosed is going to turn into V enclosed times, and this is volume here, not voltage. We'll get to voltage later on. So Q enclosed equals rho naught times volume enclosed. Well, what's the enclosed volume? The enclosed volume is going to be the surface area times the height. So this is going to be rho, and then surface area and height, and that's the Q enclosed. So our flux is going to be the enclosed charge, which is rho naught AH over epsilon naught. And we're done. That's B part 1. B part 2. Now derive an expression for the magnitude of the electric field as a function of z. Okay, now they're saying instead of just having h and h over 2, now we're going to do z. So we're going to replace, so h is going to turn into z. And they also said, now we want the electric field. Expression for the magnitude of the electric field. Now we're going to bring in the right side of this Gaussian equation, Gauss's law. And now we're going to use this guy as area A. So making these two replacements in here, we're going to have E times A equals rho naught A Z over epsilon naught. And the two A's are going to cancel. And the electric field is going to be rho naught Z over epsilon naught, which is what they told us they wanted the answer to be. Notice how they told us the answer, and we just had to show them how we got it. So we had to show first that we're going to turn h that was given into a variable z, and we're also going to use the right side of the equation, Gauss's law up here, flux is equal to electric field dA, and we're going to say the area is just A, and that will cancel out the area. All right. Now, in order to move on, I need to scroll down, and that means these guys need to go away. And I'm also going to need more space to write on, so I'll pause and get rid of all of that. Down in part C, now we're going to take that slab and put it in between two charged plates, and note that the top plate is a minus and the bottom plate is a plus. They have the same charge density, but we got a minus and a plus here, and keep in mind that this guy is a plus rho naught. That's going to matter again now. Now they've also told us a number for this, and they've told us a number for that. Oh, and they've also given us the distance between them. All right, the magnitude of the electric field inside the slab is 0 at position z naught. Okay, so if we ignore the slab, let's go over here and ignore the slab. The positive plate has a field that points up, and the negative plate up top also has a field that points up if you happen to be standing here. If you're standing in the middle, the bottom plate, the electric field points up, and the top plate, the electric field points up, because electric fields point away from positives and toward negatives. Now, this guy is positive in here. So if I'm standing right here, I have up from plate 1, I have up again from plate 2, but then if you recall from point S way back at the beginning, I'm going to have down from the slab. So this is going to be E slab, and this guy is going to be E plate. Let's see, let's call this sigma plus, and this guy is going to be E from sigma minus. And at some point, all of these electric fields are going to cancel out, which is an indication that Z naught is below the middle here. It's towards the positive plate. And this is because that we need E from Q above to be equal and opposite to E from Q below. Because if we draw a line here, the E of the top of row, and down there, E of the bottom of row, plus E of the plates, they have to cancel each other out. That's how you get electric field of 0. Again, all we're doing is vector addition here. We just happen to be doing vector addition with electric charges. Now, of course, part 2, oh, now I've got writing all over the place. So I can read this. Part 2 is going to be, okay, well, where is that going to be? All right, so if you remember from class, Gauss's law, Q enclosed, integral E dot dA, that's an E. Q enclosed for this plate here is going to be sigma A, and the area is also going to be A, but we're going to have a top and a bottom, so that'll be 2A. So we'll have sigma A over epsilon naught equals E times 2A, and those guys cancel. And the E from the bottom plate equals sigma over 2 epsilon naught. But we have a top plate also. So plus E top, sigma over 2 epsilon naught, and this guy's up, and this guy is also up, as previously discussed with how electric fields point. So then that means E total from the two plates is sigma over epsilon naught. And don't forget that they've given us a sigma. And this guy's going to be up. And what we want from the slab is going to be rho z over epsilon naught, and that's going to be down. And calculate the value of z naught. What we want is for these two guys to be equal and opposite. So what we want is E up equals E down at z equals z naught. So we're going to have sigma over epsilon naught equals rho z naught over epsilon naught. And what we're going to do here is just solve for the numerical value of z naught. The two epsilon naughts cancel out, and we have 2 micro coulombs per meter squared equals, and what was rho? Rho was, looks like 1 millicoulomb. 1 millicoulomb per meter cubed times z naught. So then z naught is going to be 2 times 10 to the minus 6th over 1 times 10 to the minus 3rd. Gets us z naught is equal to 0.002 meters, or 2 times 10 to the minus 3rd, because minus 6 and minus 3 cancel each other out. All right, we've got one more part to this problem, and then we're coming up on 15 minutes. So I need to clear out again. Calculating the electric potential difference from the center of the slab to this top of the slab. So we're going to go from z is 0 to z equals 0.005 meters, half of the 0.01. All right, change in v equals integral E dot dr, and we're going to go from 0 to 0.005. All right, and the electric field in there, oh, I erased it, I should have kept it. The electric field is going to be sigma over epsilon naught plus rho naught z over epsilon naught. And remember, I just substituted in z naught to solve for the special case where the electric field is 0. So if we're going to plug these guys, oh, and dr is going to be equal to dz, because we're just moving in the linear distance in the z direction. So let's substitute these guys in here. So minus integral sigma over epsilon naught plus rho naught z over epsilon naught, all of that, dz from 0 to 0.005. And we're going to get a minus sigma over epsilon naught z plus rho naught z squared over 2 epsilon naught. And we're going to go from 0 to 0.005. And when you plug in all of those numbers, you're going to end up with negative 2.54 times 10 to the third. And this now is not volume, this is volts. This is volts.